Today I'm going to be explaining the topic three-dimensional geometry. The specific topic is lines. So first we just have a basic recall of what we studied in 11th grade, the coordinate axes and coordinate planes. So if we consider there are three mutually perpendicular lines in space that are passing through a fixed point O, which is the origin, then these lines divided into three planes, and these lines are the x-axis, y-axis and z-axis respectively. These planes, the coordinate planes, divide the space into eight parts, which are known as octants. Next we have lines and directed lines. We've already studied this in junior class as well. A line is basically a one-dimensional figure that extends infinitely in both directions. It has no thickness and it has only length. A directed line, or otherwise also known as a vector, is a line that has a definite direction. So it has a fixed starting and ending point indicating a specific direction. Next, we have direction cosines and direction ratios. So if we take a line L that is passing through the origin, it makes angles alpha, beta and gamma with the x, y and z axis respectively. These angles are called the direction angles. The cosines of these angles would be the direction cosines. So these are usually represented by L, M and N, where L is cos alpha, M is cos beta and N is cos gamma. If we reverse the direction of L, then we get the supplements of these angles. So it will become like cos pi minus alpha and so on. Next we have the direction ratios. So let us take any three numbers which are proportional to direction cosines of a line. These are called the direction ratios of the line. If we take L, M and N as the direction cosines and A, B, C as the direction ratios of a line, then A is equal to lambda L, B is equal to lambda M and C is equal to lambda N for any non-zero lambda which belongs to R. So here we have a small equation given that is to find the direction ratios using direction cosines. And here we have the relation between them. So if you do the direction cosines divided by the direction ratios, you are going to get lambda. So understanding the equation of a line. Okay, sorry. To describe a line in 3D, we need a point A through which the line passes with coordinates x1, y1 and z1. Then we need a direction vector B which is parallel to the lines and has components A, B and C. So the equation of the line that is passing through A and parallel to B can be written in the vector form as R is equal to A vector plus lambda B vector. So here R represents any point on the line and lambda is a scalar parameter. Moving on, we have the diagram given over here, which is used for the derivation of this equation that I shown in the previous slide, and we have the same equation in Cartesian form which can be written by eliminating lambda. So how we will be getting that is writing these equations in terms of lambda and then equating them with each other, which gives us this equation: x minus x1 by A is equal to y minus y1 by B is equal to z minus z1 by C. So this form shows the ratios between changes in x, y and z along the line. Next we have shortest distance between two lines. There are two main cases over here: coplanar lines and non-coplanar lines. Coplanar lines are further divided into two sections, that are intersecting lines and parallel lines. So let's see that in a bit of detail. First we have shortest distance. First we have the shortest distance between two intersecting lines. So here we are given two intersecting lines. They have a point of intersection O. So these intersecting lines that meet at a point must be coplanar. That is a criteria. It must be coplanar, meaning they lie in the same plane. If they are not in the same plane, they cannot be intersecting. And since they are intersecting, they are touching each other, the point of intersection O. So the shortest distance between these two lines will be 0, since they are coming in contact with each other. Moving on to the second case, we have distance between parallel lines. So for two parallel lines that are in the same plane, we have this equation over here that is to give the distance between these parallel lines. So first we write line A, the equation of line A, the equation of line B, and then we get the whole equation that is used to find the shortest distance between these parallel lines. Here A1 and A2 denote the position vectors of points on each line, and B denotes the direction vector common to both these lines. Next we have distance between skew lines. So first of all, what is a skew line? A skew line are lines that are present in space. They are neither parallel nor intersecting. and they are non-coplanar. Non-coplanar as in they are not in the same plane, and the shortest distance between them is the length of the perpendicular segment between them. So we can write it, the equation for shortest distance between two skew lines can be written in the vector form as given here. So this is the starting of the derivation. Once we do the derivation, we get this equation, which is used to find the distance, the shortest distance between two skew lines. The same equation can be written in the Cartesian form, which is a much lengthier method, so we'll be not looking into that. But the equation for shortest distance is this, and in some cases we're given the Cartesian form, which can be used to reverse back to the distance form, the distance formula, which is the original formula. Next we have a few examples and applications. So in real life there are many applications of skew lines. You can see there are overpasses or the street signs over here. So if you, supposing that you draw a line on the road over here, they will never come in contact to each other, and they are obviously not parallel. They are lying in space that are in different planes. So here I have a model of it as well. So supposing we have a line over here in this plane. Next, another line we have that is in this plane. Now these will not intersect with each other. At the same time, they are not parallel to each other either. So these are skew lines that are non-coplanar. Moving on. We have a few questions that are using the applications of skew lines. So I'm going to be explaining this one. So an airplane is flying along the line, the equation is given, where lambda is a scalar component, and another airplane is flying along the line, second equation is given, where mu is a scalar. So we need to find the shortest distance between them. So here the diagram is as well given. You can see that there are two planes flying. Now looking at it from a 2D point of view, it seems like the lines intersect at this point. But when you look at it in a 3D point of view, you see that one of them is going on top, the other is going from the bottom. So they're not intersecting, and they're obviously not parallel. So the equation that I've shown for shortest distance of two lines can be used to solve this equation by using the vector components that are given in the equation 1 and then the ones that are given in the equation 2.
Any two lines in a plane are either parallel or intersecting. If the two lines are parallel, then the shortest distance between them is the perpendicular distance between them. If the two lines are intersecting lines, then the shortest distance between them is 0. Similarly, in a space also, the shortest distance between the parallel lines is the perpendicular distance between the parallel lines, and the shortest distance between the intersecting lines is 0. But in a space, there are lines which are neither parallel nor intersecting. Such lines are called non-coplanar lines or skew lines. The lines which are neither parallel nor intersecting always belongs to different planes. So they are called non-coplanar lines.
That's all I had today. Thank you. Ask.
How do they convert the vector equation to Cartesian equation?
The vector equation to the Cartesian equation, that is usually not given anywhere. The opposite way, however, can be done. If you're given a Cartesian equation for a question and you have to get it into the original, that is the regular vector equation. So that can be done. All you have to do is you have to get the vector components that are given in the equation over there. That will be given in the question usually. So once you get those components from the question, all you do is substitute them into B1 and B2 as you are given in the vector form. Once you do that, you reverse them right in terms of lambda. Once you do that, after that you're just going to have to reframe the equation, and you're going to get the vector form. The opposite is usually not there, and even if it is possible, it's beyond my knowledge, so I cannot answer that. Any other questions? Yeah, sure.
According to the information you provided,
Yes.
in order to find the direction cosine action ratio, so the vector must pass through the origin. Is it
Yes.
possible that such a situation arises where it does not pass the origin, can that vector have a direction cosine ratio?
See, first of all, to find a direction cosine, what you need is a direction angle. For there to be an angle, it has to be obviously touching with the x-axis, y-axis and z-axis. So if it's not passing through the origin, then it's not really touching all the lines. So you do not get an angle that it has with x-axis, y-axis and z-axis. So obviously that cannot give you a direction cosine.
But then we have different angles in correspondence to different planes, right?
Yes.
Alpha, beta, and
Yes.
so what if it just coincides with two planes and not the third one? Will there be a direction?
If it coincides with two planes and not the third one.
Not necessarily all three.
Yes, you can get it, but then again the third one, which is n, that you will not be getting there. Yeah. Okay. Any other doubts? Yeah, go on.
In the question you shown about an aeroplane moving with two vectors you have given.
Yes.
There was after that in the diagram you also show that two aeroplanes are flying and then they are intersecting.
Yes.
So there are two parts of the question. The one question at what points? Like how to do it? Like is it related to finding x, y, z or x1, y2, z2?
It is related to finding the shortest distance. The distance is obviously going to be just a value. It's not going to be in terms of x1, y1 and z1. Since you're not finding a point, you're finding the distance. So you're going to get it in units.
But it's not related to the coordinates, like for example x1, y, or like x, y, z, because the question like at what points they will meet or something I've read, I guess.
It's not about meeting, it's like the shortest distance. So supposing, I'll just use these. You are given two lines, okay? You have to find the shortest distance between them. These are in different planes, okay? So the shortest distance, let's say you draw a perpendicular line from here to here. This is going to be a straight line over here, making 90 degree with both the lines. So what you're finding is the distance between them. And since you're finding the distance, you're not going to get it in points from coordinates. You're going to get it in the form of units, like units as in the 3D geometry we don't have centimeters and meters, but yes, it's generally written as units since you are getting distance there. So it won't be in terms of x, y and z.
So like in the question if they ask about points, like do we have to just directly find the distance? Between the two vectors?
Yes, you have to find the distance between them, unless instead of the vector form of the equations you're giving coordinates for the 2 points and they're saying find the shortest distance between these. Then you will get the answer as a coordinate. Otherwise, it's just a straight line that you're getting distance. Any other doubts? Yeah. Okay.
Could you please tell the significance of the scalar you kept mentioning?
The scalar what?
Scalar form of a line.
The scalar form of a line.
Significance of the scalar.
The scalar component, okay, so lambda basically, right? Yes. The scalar component is important in the equation because let us say there's a line, okay? So it has obviously a vector will have 2 points. First is the direction and the second is the scalar point of it. So the direction is what makes it a vector. That's usually denoted by n cap. That gives the direction, it's a unit vector. However, we will also need a scalar to make it a complete vector. So that is why the scalar is important in the equation.